What we're going to look at is equations, and in 4.2, that's what you worked on, is what I would consider the basic trig equations. What we're going to look at now is the ones that are factorable or quadratic in nature. Okay, they're not all quadratic, but they're factorable. That's the kind of thing then. Okay, all right, a couple of questions on this. If you have a quadratic equation, which you have had in your background, hopefully, a can't be 0. Let me show you what would happen if a is 0. If a was 0, you would have, that would cancel out, you'd have bx plus c equals 0. What kind of a equation is bx plus c? It's linear, okay, so it's not quadratic. So if a was 0, then you have a linear equation. Okay, so the idea is quadratic always has to have the x squared in it. It can be missing an x, it can be missing the bx and the c, but it can't be missing the x squared. Okay, so just kind of to remind you of a few things, I'm going to do just kind of an example, an algebra example, and just kind of show you how this goes. So let's say you had something like x squared minus 4x plus 5 equals 0. I'm just going to review algebra because what we're going to do with trig is going to be very similar to that. That's a quadratic equation. You always got to make sure that one side set equal to 0. If it is, what do? You have two choices. Factor, or if it doesn't factor, where do you go? Quadratic formula, okay, which will happen sometimes in trig. So the way we would finish up this algebra example is we'd draw two parentheses and we'd factor it. Okay, now there's a lot of times issues with students factoring in this class and then even in calculus, and you got to get it down. So of course we just go x and x to get x squared. Now for 5, the only choice you have is 5 and 1, right? Okay, now the signs have got and I may have given you something that didn't factor. I may need to change that. I was trying to do that in my head. So let's see, I bet if I do this though, if I change this to minus 5, let's change that to minus 5. Okay, sometimes it's kind of in your head hard to come up with something that factors. It is for me at least. Okay, so that middle term would be 5x. This outer term would be 1x. And what are you trying to make those add up to? Negative 4x, right? Okay, you're trying to make that add up to that middle term. So what is the sign on the 5 and the 1? Yeah, negative 5 plus 1. Good. Okay. All right. And one thing about this, and I say this all the time to students, I don't know if they listen or not, but every time you factor something, you should check it because you're just wasting your time when you proceed through the rest of the problem. Okay. So what are the two answers to this problem then? 5. Yeah, x equals 5, and then x equals negative 1. And you can do that part in your head. So when we do a trig equation, we're going to do this in a very, very similar way. We're going to factor, set each factor to 0, but then the trig part comes in. Okay? All right, does everybody remember that kind of equation? Yes. Okay, all right. So factoring is going to be very important in this section. And on the gateway test, this problem number 1, this is a really good example of the kind of thing you'll see on the gateway test. Okay? It's factorable. How do you know it's factorable? Well, it's got a cosine squared in it, so it looks like a quadratic equation, kind of, doesn't it? It has a squared term, a middle term, one side equal to 0. So the way we're going to start this is we're going to draw two parentheses, and we're going to factor. And a lot of times students, although they can factor a trinomial okay, when it comes to this thing having cosines and sines in it, it looks different to them. But trust me, it's not any different. So the first term is cosine squared. So what would you use? Cosine times cosine. Okay? So you put that in. So we say cosine x times cosine x is going to give cosine squared x. So we know that. Okay, then the last term's 1. So what are you going to use? 1 and 1. Okay. Now what you got to do is just make sure the signs work out the right way. And you don't have to write this visual out. That's just one cosine. This outer term's one cosine. What are you trying to do with those two things? You're trying to make them add up to 2 cosine, right? How do you do it? They're both not plus or minus, but both plus, right? 1 plus 1's 2. Okay, so we got that. So we've got that. Now they're the same factor. So what we do now is we just take each factor, we set it equal to 0. Now, hopefully it would make sense that I don't need to solve both of these equations because they're the same, right? So if I solve one, then that should give me the solution to the other one. So what we're going to do is, okay, we just do it one time. So we're going to isolate. This is kind of like what you did in 4.2. You would move the 1 to the other side, so you'd have this, okay? Now you want to do this independently of a calculator. You want to just reason this out on a unit circle. So if you look at this statement, what are you looking for? You're looking on the unit circle and figuring out where x is -1. Where does that happen?
Pi.
At pi, right. Okay, at that point. So if you go to that point over here, which is represented by pi radians, that would be where the cosine takes on that value of -1. So then that would be a solution to the problem. And there's a couple of ways that I can ask these questions. I can say, solve on an interval, which is what I'm saying here. So I'm saying, give me all the answers from 0 to 2 pi. Is there any other place from 0 to 2 pi where the cosine's -1? That's it. Okay, so that is the answer, and it's the only answer. Okay, so what we would do is we just write our solution. We write a solution set, so it's pi, and that's it. Okay, now see, I didn't have to touch my calculator or anything. One thing I did when I put this together is I did some of this on a graphing calculator. I encourage you to, a little bit on your homework sometimes, to graph some of these and see what turns out on this. So like this graph, you do not need to write this graph down, but what I put in my calculator is I put in like cosine of x squared. That's how you have to put it in on a TI. You have to have parentheses around cosine x squared. Then I do plus 2x plus 1. What you want to do to check this on a graphing calculator is you want to graph this side, leave that side 0. Then what you're doing is you're looking for an intersection point. So the intersection point's pi, or not an intersection point, a x-intercept. So if you looked at that graph, the only place it touches the x-axis is at pi. So it's right. So if you put that in your calculator, you could trace at your answer pi, and you could tell it's right. And what I did on my calculator is I made my window go like this. So I just went with a kind of a standard window, took that out to 2 pi, and then that proves it's the right answer. So I'm going to show you graphs on a lot of these problems as I go through these today. Okay, does that problem make sense to everybody? Okay, how do you know to factor? It's got a second power in it. So almost all the equations in this second are going to have powers that are 2 or higher. Okay, so let's go to this next one here. Okay, so with this one, here's the deal. You see a second power. Automatically, that needs to make you think, I need to solve this by factoring. But in order to do that, what does one side have to be equal to? 0. So you must do that first. Okay, so what I'm going to do is I'm going to move the sign to this side. One of the things I like to do is whatever my squared term is, I always like to have that as a positive number in front. So I'm going to do that. Okay? Now, you might write this, because I sure do see students do this, and I see students do this all the time, just because it seems logical, but it's totally wrong to go through and divide both sides by sine. Okay, it seems logical, but it's, you know, what'll happen is you'll lose one of your solutions, or 2 solutions or something. You don't generally ever want to divide by variables. So don't do anything like that, because you're going to lose answers. Okay, what you want to do is do this, now factor. Okay, so how would you factor that expression? Yeah, it has a sign, it has a common factor, right? So this one has a common factor. Conceptually, this is no different than having something like 2x squared minus x equals 0. If you were to solve this, like in a college algebra class, you would take a 2 out, and then you would solve it from there. You do the same thing here. Your common factor is a sine, so you take sine x out. Then in the parentheses would be 2 sine x minus 1 equals 0. Okay? Distribute that in your head. that works out, factor, so you factor and you want to check. So what do you do once you factor it? You set each individual factor to 0, and then you solve it. And this is the kind of thing that you did in section 4.2. So that's a factor, set it to 0, solve it. That's a unit circle problem. Then you have 2 sine x minus 1 equals 0. Look at the unit circle and figure that out. So I'm going to just isolate the sign. So I'm going to have 2 sine x equals 1. Then I'm going to divide by 2. So I'll get sine x equals 1/2. So what I'm going to do as I'm doing these problems, I'm going to draw a unit circle. Now, if you're doing your gateway test, for example, I do give you a blank unit circle to fill out on the gateway test if you choose to do that, but I don't grade it. So just kind of be able to work this out on the spot. Okay? If you're trying to figure out where the sign is 0 on a unit circle, what are you looking for? You're looking at the y value. So there are 2 places on the unit circle where y is equal to 0. One of those places is here. The other place is here, right? So what are those angle answers?
Pi 2 pi.
Pi 2 pi. Now I think on this one, I think the interval, if you look at the directions to the problem, my directions to the problem were 0 to 2 pi, but don't include 2 pi. Pay attention to that on the gateway too. Don't give me 2 pi because it's wrong, and that would count as a mistake. So you would want to give, one answer would be 0. This answer would be what? Pi. So that's 2 answers to your problem right there. Okay? All right? So you're doing what you did in 4.2, except the factoring is what's new. All right. How many places on a unit circle would the sign be equal to 1/2? In other words, where's the y value 1/2? Up there, right? The sign is positive in quadrants 1 and 2. So you're going to have an answer up here, and you're going to have an answer up here. You just got to figure out what that is. Well, you're going to have a point on a unit circle that is square root of 3 over 2 1/2, and that corresponds to a 30-degree angle. If you look on the unit circle, then you're also going to have a point in quadrant 2 that is negative square root of 3 over 2 1/2, and that has a 30-degree reference angle like that. Okay, so you got to name those 2 answers, but you got to name them in radians. So 30 degrees in radians is pi over 6, and then this one is 5 pi over 6, like that. Okay, I remember there's several little tricks that I've shown you to do on this. You can count by pi over 6. You can go 1, 2, 3. Hold on, I got too many there. 1, 2, 3, 4, 5. You can count over like that. Or you could take 150 and multiply it by pi over 180 and reduce it if you have to. Okay? So those would be all of the correct answers of the problem that fall on that interval there. Okay? So the thing about it is, most of the problems unit circle again, right? Okay, for the 100th time this semester, right? You see it over and over again in trig. Now what I did on the graph is, and I'm just showing you graphs. I didn't want to take up a lot of time to put these in a calculator. But what you would find when I did this on the graphing calculator, I set my window going from 0 to 2 pi, and I think I had my y going like -1 to 1. So notice on this, 0 was an answer. I think pi over 6 was an answer on this. That was one of them. Then I believe 5 pi over 6 was an answer, and or pi was. No, I think I may have something wrong on this. I don't know if I got the right graph in there on. Yeah, I do. I got the right graph. But anyway, you would have one of these answers is going to be like 0. I think I may have put the wrong thing. I got the right thing in the calculator. You know what? That's the wrong graph. If you look at this, I put this totally wrong in the calculator. This should be like this. It should go sine x squared minus sine x, like that. I'm going to pull up my calculator and just show you that, because I do want to have you guys maybe do a couple of these on the calculator with me. So why don't you get your calculator out if you have it, And let's just do a checking on this one, and then that'll kind of give you some ways to make sense of these problems. So actually, the way you do this, first thing you want to do is you want to go to, make sure you're in radian mode. And then when you put this in your calculator, it's got to go like this. Okay, you got to put it in. One side's equal to 0, so you got to put 2 parentheses sine x, double up on the parentheses, then square it. So that's how you have to put sine squared in. You have to have a parenthesis, sine x in the inside of it squared. Then I'm going to do minus sine x, like that. So that's what we're going to graph. And for your window in radians, you want to go like this. You want to go 0 to 2 pi. Remember I said that I want you to solve it on the interval 0 to 2 pi. Pi over 2, it doesn't really matter what your scale is for this, but let's just do pi over 2. That way we're going by 90-degree increments. And then the y window is up to you. It doesn't really matter. I'm just going to do like -2 to 2. All we got to see is the x-intercepts, okay? So if you put this in and graph that now, you should see all of the answers we got, okay? And this is kind of a good thing to do a little bit on your homework here. So notice that 0 was an answer. Does it look like 0 is an x-intercept? It is, okay? So you could trace 0. That's right. Then you could go trace pi over 6. Okay, that's another answer. That checks. See, it's blinking where it's supposed to. Another answer was 5 pi over 6, so you can go 5 pi over 6 like that. That's blinking. That's right. And then the last one was pi, like that. Now that's it. Okay, you can do that on every single one of these problems if you want to. Right, did that make sense? Okay, so solve them algebraically. But, take the attitude of checking at least some of these when you're doing your homework, verifying that they're right, okay? All right, any questions? Okay, so let's move on to this one with the cosecant in it now. Oh, what did I just do? Okay, all right. Okay, so let's do the cosecant. All right, now, the reason you're going to know to factor this is, number one, there's a 5th power in it. When the powers are higher than 1, factoring is the attitude you're going to take, and then one side set equals 0. Okay, so how would you factor this? It's got a common factor, doesn't it? You go with the one with the lowest exponent. Like if you had, in an algebra class, if you had this problem, what would you do? You'd factor an x out. Okay, so you'd have x times x to the 4th minus 4 equals 0 if you did that, right? Okay, so you're going to do exactly the same thing here. Take a cosecant out. That's going to leave you cosecant to the 4th x minus 4 equals 0. At least in your mind, multiply it out and make sure you've done that right. Okay? Now, there's a couple other things you could do. There's a couple of things that you could think about. And again, this is where factoring skill comes into play. Does something like x to the 4th minus 4 factor? Yes. Yeah, what do we call that problem? Difference of 2 squares, right. So you can do this problem this way if you want to. Like you could draw 2 parentheses and say x squared times x squared. 2 times 2, that's a perfect square. And then remember the signs go plus minus. Do you guys remember that? You need to, because it's going to show up. Okay. So I'm going to go ahead and factor it one more time. I'm going to write this as cosecant x, and then this thing is 2 squares. Okay, it's got an even exponent, and 4 is a perfect square, so we can go cosecant squared and cosecant squared, 2 and 2, and then plus and minus like that. Now you could bypass that, and you could just set cosecant to the 4th x minus 4 equals 0 and solve it, and you'd still get the same answers. Okay. So what I'm going to do now is we're going to set each factor to 0, and then we're going to interpret this on the unit circle primarily. So I've got cosecant squared x plus 2 equals 0. I'm going to work with that. Then cosecant squared x minus 2 equals 0, like that. Okay? Now there's a couple of approaches you can take on this. if you have a cosecant, you can still go to the unit circle. You could even change those to sines if you want to. I'm going to leave them the way they are, and let's just try to figure out and interpret how this would go on a unit circle. All right, so the cosecant's definition is r over y, right? You got to figure out on a unit circle where r over y is 0. So I want you to think about that for a minute. In a unit circle, r is always 1, right? Is there any place where 1 over y would give you 0? No way. No way, because the only way you get 0 out of a fraction is if you have a 0 numerator, right? We have 1 as a numerator, so there's no solution to this problem right here, okay? So another way to look at this is, what does your cosecant graph look like? It's the one that sets on top of the sine, right? The cosecant graph's the one that has these U-shapes, up, down, over and over again. It never touches the x-axis. There's no place where the cosecant's equal to 0. Does that make sense? Okay. When you solve these problems, a lot of times those factors are going to provide no solution. That's an example of one. Okay, let's do this one. Let me show you what happens on this. We're going to have cosecant squared x equals -2. How do you make that square just become a regular cosecant? You square root both sides, right? Okay, so you're going to square root both sides, and look what happens. You're going to get, well, that's going to be cosecant x, but you've got a square root of a negative number. Okay, we're not dealing with negative numbers, we're dealing with real numbers, so again, no solution. This is a very common thing that happens when you're solving trig equations. Okay, so we got that. So far we have no solution. So we got one more chance here. We're going to solve this equation. So we're going to isolate the cosecant like that. Then we're going to take the square root of both sides. When you take a square root of both sides, you need to be sure that you pay attention to the fact that you have a plus or minus square root of 2. Okay? You have to, because if you don't, you're not going to get all your solutions. Okay, does this look okay so far? Okay. Now, if it's got a square root of 2 in it, well, it's pretty likely that this is going to fall at 45 degrees, where we have square root of 2 over 2 square root of 2 over 2, which is a pi over 4 or 45 degree angle like that. Okay, so one of the things that's going to happen on this, you can double check this if you want to, the cosecant of pi over 4 is really just going to be the reciprocal of the sine. The sine's square root of 2 over 2, so that means the cosecant's going to be 2 over root 2. Then if you rationalize that denominator, so you're going to get 2 root 2 over 2, so you get 2. I'm just checking and verifying that, right? So that would be an answer. Now, how many answers are you going to have if it's plus or minus root 2? You're going to have 4, right? You're going to have one in every quadrant, so you're going to end up having, you know, this point where it's negative root 2 over 2. Still going to have a reference angle of 45. Okay, and then you're going to have one down there, and you're going to have one down there. So it's going to be there's going to be right in the middle of every quadrant. So those solutions are going to be pi over 4. Okay, then you got to get this one. Now you can count by pi over 4s. It's just 1 pi, 2 pi, 3 pi over 4. 4 pi, 5 pi over 4. And then 6 pi, 7 pi over 4. Okay, or if you can refer to your unit circle when you're doing your homework. I don't care if you refer to a unit circle, because it'll save you time. But for testing purposes in the gateway test, you want to be sure you don't have to do that. Okay, so that's the idea. All right, does that make any sense? It's all about factoring. Now, see, I went ahead and graphed this on my calculator, and what happens on this is pi over 4, this is 3 pi over 4, this point right here is 5 pi over 4, and that point is 7 pi over 4. So it's checkable. If you put this in your calculator, now notice the way I put this in my calculator is I have to do 1 over sine, and I have to do 4 over sine. I got to change the cosecants to sines, and then that's the graph that you would get. Okay? All right, you guys got any question about that? Okay. All right, so I'm going to let you guys try a problem here next. So try this one, number 4. That's a great gateway problem right there. That's typically the kind of things we get. Factorable, make sure one side's equal to 0. And I'm going to ask you again, how do you know that you factor? What do you look for? What do you see? Second power or higher. That's important. Okay, it's powers. All right. And then I put a graph on here, and you should. You can, if you want to try to graph this on your calculator and check your answers, then by all means do this. This is a pretty standard problem right here. That you do that. Okay, so how did you factor this? Take a sign out, so you have a common factor. Don't forget about common factors. So you're going to have sine x times sine x plus 1 equals 0. This one's pretty simple to do. So then you're going to set the first factor to 0, interpret that on the unit circle. And then the second one, interpret the unit circle. And then this one you could isolate the sign so that you get this. So here's what you do. Okay, on a unit circle, where is the sign equal to 0? 0 and pi, exactly. Okay, it's where the y value is equal to 0. So one answer is going to be 0 without a doubt. The other one is going to be pi without a doubt. Okay, so that's how that goes. Okay, how many places on the unit circle have a sign that's equal to -1? Just one, and that's down, isn't it? Okay, so that would be at the point here where you have the point 0, -1. What's that angle? 3 pi over 2. So there is your answers to your problem right there. Okay, that one's pretty easy. What's that?
Even though it's out of range.
Well, okay, the directions to the problem said solve the equation on the interval 0 to 2 pi. Include 0, but 2 pi is out of range because of the parenthesis. Okay, you would find that, yeah, 2 pi would be another place where the sign is 0, but it's out of range. So pay attention to that, okay? That's real important, okay? And basically on the graph that I put on here, those are the 3 solutions. That's 0, that's pi, that's 3 pi over 2. So you can trace them out and make sure you're right, okay? All right, any questions about that? Okay, and if you're going to take Calc 1 in the future, we've been doing that a lot in my Calc 1 class. We solve trig equations, and students a lot of times, when they don't know how to do them, it's a disaster. I mean, I understand people forgetting stuff, but the better you get it down now, the better it's going to be for you in the future if you're going to go that way. Okay, now, the next kind of stage I'm going to look at is sometimes you have to use identities when you solve equations. Now, like this one, the clue kind of is you have a sine and a cosine. You have 2 trig functions in the same problem. What you would like to do is to make sure that it just has one function in there, okay? So what I'm going to do on this is we have an identity that could turn that sine into a cosine, right? Okay, so what we're going to do is we're going to use that identity. So we have sine squared of x plus cosine squared x equals 1. So since I already have a cosine here, it makes a lot of sense to just change this sign. And you don't have to write this identity down. You've done this enough that hopefully you just kind of do that in your head by now. So what I'm going to do is I'm going to replace the sign with what it's equal to, 1 minus cosine. So I'm going to go up to my problem, bring down the 4, and use a set of parentheses and replace the sign with 1 minus cosine squared x, and then leave the second side, the right side, alone when you do that, because now you've got one trig function in the problem. So now we're going to kind of clean it up, get one side equal to 0. Then it's going to be very similar to the other problems. So do a distributive property. That's going to be 4 minus 4 cosine squared of x is equal to 4 cosine of x plus 1. Okay, now you see that it's going to be a factorable problem, so you need to decide which side you want to get equal to 0. Now here's my thought process. Okay, because that squared term has a negative, I'm going to take it to the other side. I always like to have the number in front of the highest power term having a positive. So I'm going to make this side, and you can do it the opposite way, it doesn't matter. I'm going to make this side 0. So I'm going to move this over here to make that positive 4 cosine squared x. Going to leave all this stuff on the right exactly the way it is. And then I'm going to move the 4, so I'm going to subtract 4 from both sides to get that. Okay? To me, it just makes factoring easier if you do it that way. So you've got 0 equals 4 cosine squared x plus 4 cosine x minus 3, like that. So then we've got the left side equals 0. Okay? All right? Does that look okay, what I'm doing? Okay? So use identities, okay? There's going to be times when you have to use identities to solve these equations. So now we're ready to factor. This tends to be the kind of factoring problem that students often struggle with more when you have a number in front of the squared term. So you have two choices here now. You could go 2 cosine and 2 cosine, or you could go 4 cosine and 1 cosine. You just kind of have to trial and error this. So I'm going to start this way. I don't think this works, but I'm going to start this way. So I'm going to do 2 cosine x and 2 cosine x. Well, this might work. I may be right now that I look at it. Okay, you can't really do this problem in your head. You have to write something on your paper. So I got 2 cosine, 3, and 1. Now you got to make sure the sign works. Now if students would take more time to just do this until they get real confident in their factoring skills, they'd do better. Just write those two things down. What are you trying to make the 6 and 2 add up to? The middle term, the inside term. So you're trying to make that add up to positive 4 cosine x. So what is the sign of 6 and 2?
Minus 2.
Plus 6 minus 2, right? That makes it real clear if you take your time to do that. So we've got a plus 6 there and a minus 2 there. So that means you're going to have a plus there to get the positive 6 cosine. You're going to have a minus 2 to get that. Okay? So we got down to the factoring. A little harder problem because of the identity in it. So now what do? I set each factor equals 0 and solve. Okay? All right, so I'm going to go ahead and do that. I'm going to do the first factor is 2 cosine x plus 3 equals 0. We'll work with that. Then the second factor is 2 cosine x minus 1 equals 0. So we're going to solve these two things right here. Okay? All right, so I've got my factors. Is the factoring okay with everybody? Okay. Now we're going to solve this. So I'm going to subtract 3 from both sides. That's going to give 2 cosine x equals negative 3. I divide by 2. So I get cosine of x equals negative 3 over 2. Now this happens lots of times on these problems. Okay, is there any place on a unit circle where the cosine would reach negative 3/2? No. How come?
The range of sine is negative 1 to 1.
Right, exactly. The smallest number for a cosine is negative 1, right? That's the smallest x value. That's smaller than negative 1, so this has no solution. Okay, and this is going to happen a lot. Don't freak out when that happens. This just happens. Okay, that doesn't exist. So forget that one. And then this one, we're going to add 1 to both sides. So we get 2 cosine x equals 1. Then you can divide by 2. So we get cosine of x equals 1/2. Now, how many places does that happen?
2.
Yeah, it's 2 places on a unit circle. There's 2 places where the cosine's positive. Those 2 places are quadrant 1 and quadrant 4. So you just need to figure out which angle has an x value of 1/2. You can look that up on the unit circle. So that's actually 60 degrees as a reference angle. And over here it would be the point 1/2 negative square root of 3 over 2. So that would be a 60-degree reference angle there also. Okay, now you can look up the radians and do that because we do want radian measures on this. So 60 degrees is pi over 3. So we have that. And then this next angle here is really 300 degrees, right? You can look it up on the unit circle if you want to. Or you can just convert it. Don't forget that you can convert. So if you multiply it by pi over 180, you get 30 pi over 18. Then I think you can divide by 6. and they get 5 pi over 3. So those are your two answers right there. Okay. Okay, now see, it'll speed up your work a little bit if you refer to a unit circle as you're doing these problems. Okay, and the graph that I put on the calculator, I was just going to show you that is pi over 3, and that right there is 5 pi over 3. You guys don't need to write the graphs down. I just put these on here because I wanted to mention that as we go through these problems so you can visually see what you're doing. Okay, so I used an identity. That's kind of the next stage that you have to go through. How do you know to use an identity? Well, usually, not always. If you have two trig functions and you're having trouble factoring it, then an identity is possibly a good way to go. There's little differences on these problems, and sometimes you have to be willing to try something. Okay, so let's look at the next one. Now, this is another example of one that you have to use an identity on. And again, it's got two trig functions. Now, trying to write a sine and a cosine, you don't really have anything that you can do with a sine or a cosine. But what you want to take advantage of is trying to change it into a sine. What's that? Did I do something wrong?
We have sine squared x minus 8 sine x.
You don't have this problem on your handout?
I got that wrong.
What do you have?
I printed mine off though.
Oh, okay. I gave a different one today. I may have marked off a few of these. What do you have on yours, Austin? You have... I did.
I have the same.
Yeah, 7.
Here. Is this a new one?
How the heck does this stuff happen? Oh, I know what's going on. I think I
Here.
trimmed off a
Here's
few
the difference.
problems here.
Oh, okay.
We're okay. We just trimmed off a couple of problems, okay? Well, I'll tell you what, I would like to go ahead and go through this problem. Then I think what I did is I probably took that off. So, well, you don't need to write this down, but you can pay attention to this if you want. I'd like to go through this problem because it's kind of a little bit different thing to look at. So if you don't have that on there, you can write it down. If not, just pay attention to it if you want to, okay? So I did want to show you on this, sometimes it's beneficial to square both sides. You probably see this in your homework somewhere too. And the reason I'm going to square both sides is because you can do a lot more with a sine squared and a cosine squared, right? You can take advantage of that identity, sine squared theta plus cosine squared theta equals 1. So a lot of times squaring both sides of an equation comes in handy. So when you square this side, now you could write that out twice and FOIL it, or you can learn to do it in your head. You just square the first term. So if you square a sine, you get sine squared theta. You square the 1, you get a plus 1. But then to get that middle term, you got to take 1 times sine theta, then you got to double it. So if you're confident in doing this shortcut, go for it. You'll save yourself a little bit of time. If you aren't, just write it out twice and FOIL. So that's what that is. Now when we do the right side, this is not a FOIL problem because that's not square root of 3 plus or minus something. So you just do this. What is the square root of 3 squared? 3, okay. And then cosine squared is cosine squared theta. So a lot of times I see students on a problem like this, they mess up with the algebra more than the trig. So you got to get everything multiplied out correctly. Now what we're going to do in this is it would probably be wise to do what with that cosine squared? What do you think? Change it to 1 minus sine squared. How come? Because then you've got nothing but sines in your equation, and that makes it easier. Since I've already got sines here, so what I'm going to do is just bring this down. That's sine squared theta plus 2 sine theta plus 1 is equal to 3. And then I'm going to replace this with 1 minus sine squared theta like that. Okay? Then I'm going to finish this up. I got just going to leave this side like it is. So that's sine squared theta plus 2 sine theta plus 1. This side you want to multiply out, so that's going to be 3 minus 3 sine squared theta, like that. And then you're ready pretty much to get everything on one side set equal to 0. Okay, so I'm going to just write the left side as it is. Okay, then I'm going to move everything over here. So that's going to be minus 3. Move this over there. That's going to be plus 3 sine squared theta equals 0, like that. Okay, and you don't want to mess up here, because if you mess up, then it's probably not going to factor. And this problem's probably designed so it factors. So you have some like terms. We're going to put those together. So that's going to be 4 sine squared theta. So those go together. Then we're going to have plus 2 sine theta minus 2 is equal to 0. Okay? So let me pause there for a second and see if you guys got any questions about what I did and why I did what I did.
It's 5.
What's that?
You put 4 sine squared theta. Isn't it 5? Because
Well, I combined the like terms is what I did. Okay?
You're right.
And I think I got everything right on there. Okay? All right, so what I'm going to do from here, now you could go ahead and factor it now if you wanted to, but I want to see if you notice what I notice. What do you notice? They all divide by 2. Divide by 2. You can divide by a constant, so it's okay to divide everything by 2. Just don't divide by a variable, okay? And that just makes the factoring easier. So this is going to give 2 sine squared theta plus sine theta minus 1 is equal to 0. Now you're ready to factor it. Does it make sense to you guys why I squared both sides? Okay, I introduced a sine squared because then I have an identity. If you don't do that, you can't really work with any identities, okay? All right, so let's go ahead and factor this up here. So I'm just going to factor, we're working with this trinomial right here. So what we're going to have is 2 sine theta and sine theta to get that first term. The last term's 1, so we can only use 1 and 1. And then the sign's got to go like this. They're going to have a plus there and a minus there, because you're going to have a 2 sine and a minus 1 sine to get a plus 1 sine. Like that. In your head, make sure that you've done everything right. Okay, now from here, pretty similar to what we've been doing on these, is set each factor to 0 and then solve. Now I think that the directions on this problem also say give me angle answers. So you got to pay attention to that too. Usually you're going to give radian answers, but sometimes you can give angle answers. Okay, so if we do this, this factor you can rearrange in your head. You would have 2 sine theta equals 1. Then you can divide by 2. So you'd have sine theta equals 1/2. Okay. Then this one you can isolate the sine and get sine theta equals -1. All right, now what does you do? You go to the unit circle and figure it out. You're going to do this over and over and over again. So once you've got your unit circle down, this part will be pretty easy for you, hopefully. All right, how many places on one lap around the unit circle is the sine equal to 1/2? And what quadrants? Up there, 1 and 2. Okay, so you need to figure out where that is. One place that is at the point square root of 3 over 2 1/2. Which is a 30-degree reference angle. Now remember, they want the answers on this problem in degrees, so that would be one answer, right? Other place is at this point, which is the point negative square root of 3 over 2 1/2. What is that angle?
150.
150, good. Okay, you got to give the 150. Don't give the 30. We already gave that. That's a reference angle. So that's 150 degrees, okay? And where on the unit circle is the sine in degrees equal to -1? It's down here on the y-axis, good, 270. So at this point here, you got 270 degrees, like that, okay? All right, I usually don't, that's probably not a great test problem. That's a pretty good homework problem, okay? Because sometimes you have to do stuff like that, like square both sides, or use an identity. So I did want to give just a couple of examples of that. Is there any question on that? Now see, everything I've done so far has gone directly to the unit circle, and that's to help you practice and be able to do some of these without having to rely so much on technology. There's going to be times when Well, you got to use technology. And then there's times when you got to use the quadratic formula. So I'm going to do a couple of things with quadratic formula here to finish this up, and then I'm going to do a couple of things with a calculator. Okay, so here's what the deal is on this problem. I think you guys have this. This is probably your number 6, right? Okay. So what we have to do on this one does not factor. If you tried to factor, factoring doesn't work. So if factoring doesn't work, you have to use the quadratic formula. And, you know, I've written the quadratic formula here, so you want to be sure that you remember the quadratic formula. So the way that you go about doing this is you have to do a substitution. A lot of times students just immediately think that C is 4, B is 8, A is 1. No, that's not right. Not yet anyway. Okay, first thing you need to do is you need to do a substitution. You just pick a variable. I don't care what the variable is. Let's say that variable is, what do you want to do? Let's not use A, B, C. Let's use P, okay? That's called a dummy variable. It's not because it's dumb. It's just because it's whatever you picked, okay? So what you're going to have is you're going to change this equation to P squared minus 8P plus 4 equals 0. And the substitution is P is equal to sine x. And that's going to be actually an important part of this problem when you do this. Okay? So now you go to the quadratic formula. And you solve the quadratic equation, P squared minus 8P plus 4 equals 0. So you do got to go to the quadratic formula now. Did I miss something? Oh, minus 4. Okay. Okay. Yeah, I don't want to do that because there's a lot of work that you have to go through in the problem. Okay, go ahead and plug into the quadratic formula now. Okay, so the variable P is going to be equal to negative B. B is the number negative 8. Then you've got the square root of B squared. Then you got 4AC, so A is 1. C is negative 4, all over 2 times A. And this is going to be a problem we're going to end up ultimately using a calculator on. But you got to at least do this part right here on the quadratic formula. So let's go ahead and crunch this out. So it's going to be 8 plus or minus square root of 64 plus 16 over 2. So that's going to be 8 plus or minus square root of 80 over 2. Okay, you guys remember your quadratic formula? Now, don't even bother simplifying this, seriously. What I'm going to do is get my calculator out, and the only way to solve this is to use your calculator. So I'm going to go ahead right now, and if you want to do this with me, you can. I'm just going to get the 2 answers to this quadratic formula in decimals, and I'll round it off to maybe like 4 decimals or something like that. So the first thing I'm going to do is I'm just going to go 8 plus square root of 80. Don't even bother breaking that 80 down into perfect square factors. Get that answer, divide by 2, and record it. So that means that one of the answers to the quadratic formula is going to be approximately 8.4721, like that. Okay? I did that in 2 steps. Now I'm going to do 8 minus the square root of 80, like that. Get the answer before you divide by 2. And then we're going to record that. So that is approximately negative 0.4721, like that. Okay? So you have to do that, okay? You don't, otherwise you aren't going to have any success doing this one on the calculator. Right, does that make sense so far? Okay. Now, you cannot forget about this thing right here. See, I found what P is. P is these decimals. So to finish up this problem, you have to say sine x equals one of these. And then we can do that on the calculator if we need to. Hopefully you don't need to on that one. I hope you know what the answer to that is already. Then we do this, and we got to do them on the calculator. Now we're going to do this in degrees. The answer, they said they want the answer to this problem to be in degrees. So I'm going to go to degree mode, and then we got to do this. All right. So, can you think of a place on the unit circle where the sine is equal to 8? No. What's the biggest value the sine ever hits? 1. This one right here has no solution. Suppose you didn't see that. If I did inverse sine of that number, 8.4721, I'm going to get an error. Okay? It's no solution. So forget this one. Now, do this one. To get this answer, you've got to say x is equal to the inverse sine of negative 0.4721. So we do inverse sine negative 0.4721. It's going to give you a negative angle because the range of the inverse sine is from negative 90 to 90. So we're going to get negative 28.2. Let's round it to 1 decimal. So we got that. So we have negative 28.2 degrees. All right, now we're not done because you have to give me the answers on this interval from 0 to 360. So here's what you got to kind of think about in this problem is on a unit circle, first of all, what are the two quadrants where the sign is negative something? Quadrants 3 and 4, right? So you got to give me a quadrant 3 answer and you got to give me a quadrant 4 answer. What the calculator gave was a reference angle. And remember, reference angles are always positive. It gave a negative angle because the inverse sine is on that range, okay? So what we got to do is do this. So how would I find the quadrant 3 answer on the calculator? I would do 180 plus the reference angle, right? Okay, so I'm going to do 180 plus that reference angle, which is 28.2. And then that'll give one of my answers is 208.2. That's my quadrant 3 answer. Okay, and if you want to find the quadrant 4 answer, what do?
360 negative.
Yeah, 360 less the reference angle. So you need to go 360 minus the 28.2. And then the other answer is going to be 331.8 degrees like that. Okay, that's it. Okay, so you can use quadratic formula and calculator to do these. Every now and then you have to do that. So see, the key thing that I had to do was I had to kind of do a substitution that I did here. And once I did the quadratic formula, that doesn't give the answers. A lot of times students give me these as the answers. Now you got to go one step further and use that sine of x. All right, does that make any sense? Okay, now if you didn't have your calculator, you wouldn't be able to figure that one out, okay, at all. All right, now do I have this problem on my handout or did I leave this one off too? I can't remember. Is it on there?
Yeah.
Cosine squared x plus cosine, is that one on there?
It's number 8.
Oh, okay, so go ahead and I'll let you guys take a few minutes and see if you can solve this one, okay? Get your calculator out because you're going to need that. And then there's just a few more. Have you guys got your quadratic formula done here? Okay, so and I assume that shouldn't be a problem area for you. So when I did that on the calculator, I got, now you guys are already raising your hand, which means I messed up.
The
Possibly.
first one, 1.2361, you did divide by 1.
Okay, let me try that again. Okay, thank you. -1 plus square root of 5. Okay, then get the answer and then divide by 2. Okay, is that better?
Yeah.
Yeah, that's way better. Okay, I wouldn't have got an answer on mine, would I? Okay. Did I get the other one right? Okay. Okay, so we got that, all right? So the quadratic formula, you guys doing okay with that? Okay. Now what do? Got to remember this substitution. So this is the thing that students forget a lot of times, is you got to do cosine x equals 0.6180. And you got to do that on the calculator. Then you got to do cosine x equals -1.6180 like that. Okay, so far okay? Okay. What is the answer to this one without looking at your calculator? Yeah, no solution. Okay, so that one can't have, there's no such thing as a cosine of an angle being below -1. So that's no solution, so you can forget this one. And then this one, you're just going to go to your calculator, again in degree mode, and do the cosine, inverse cosine of -1. No. What am I doing? -0.6180. And this is going to give you a quadrant 2 answer, because what's the range of the inverse cosine? 0 to 180. This is the part of the problem that a lot of times students overlook. So you got 128 is one of your answers. So when we put this in, let's just round this to 1 decimal and use 128.2 degrees, like that. Okay? Now what I'm going to do from here is there's 2 places where the cosine is negative.
How did you get 128? What's the do cosine -1 of 0.6180?
Oh, I put a negative in there, didn't I? Okay. I'm blind. I'm not sorry. I'm having trouble. Okay, so I got inverse cosine of 0.6180, quadrant 1. How about that? Is that better? Okay, sorry about that. Okay, so what we have is a quadrant 1 answer. Let's just use that as 51.8 degrees. Okay. So where are the 2 places where the cosine is equal to a positive number? What are the 2 quadrants? 1 and where else? 4. Good. Okay, so we've got the quadrant 1 answer. The calculator gave that. So how do you find the quadrant 2 answer?
360 minus 51.
Right, all the way around the circle, 360 minus 51.8 gives 308.2. So that's your second answer.
What? 308.2?
Yep. Because what I end up doing is, you know, the quadratic formula, the one that makes the difference, is this one right here. So again, I went inverse cosine 0.6180, and that gave the quadrant 1 answer. Now you got to be in degree mode. Check your mode on this. You're supposed to give me degree answers on this problem. That's the directions to it. So make sure you're in the right mode. Okay, some of you seem confused or something. Okay, what did I do? The cosine is positive in 2 quadrants. And it's positive where x is. So it's positive in this quadrant and this quadrant. So what did I do? I did 360 less the reference angle. See, the reference angle is what came out of the calculator. So when I did 360 minus 51.8, that's where I got the 308.2. Okay? All right, you guys got any questions? Okay, all right. Well, I'm going to finish up this last thing here, and then I'm going to maybe start us into the next section here a little bit. But I wanted to do this section today because of the gateway test. So this one is really a trig equation where you have to use an identity. It's just, if you're going to go on get into engineering and physics and stuff like this, you know, you'd work a lot with formulas and stuff. So without going through all the details, this is supposed to represent some sort of a spring that's oscillating, and the equilibrium is P equals 0. So for our purposes, I want you to just set P equals 0 without going through the physics behind this. The reason in the real world that we use trigonometric functions to represent springs is because they oscillate. They go back and forth between different numbers. They have a down point, a low point, a high point, and so forth like that. And the equilibrium point's kind of like the midpoint of a sine wave. So it's going to oscillate. But the key thing for us is I want to see if we could figure out how to solve this equation. Okay? Well, the first thing I would do is get rid of my fraction 10. So I'm going to multiply both sides by 10, and then that's going to give 0 equals, that's going to cross that out, equals sine 2t plus sine t. Okay? So I want to see how observant you are. Now you cannot factor this. Okay, you can't factor, sine 2t and sine t are totally different entities. But is there anything that you remember about sine 2t?
That's a double angle.
There's an identity, right? Okay, there is an identity that might come in handy. Let's write it down and think about it, okay? The sine 2t identity, do you guys remember it? Some of you do. 2 sine t cosine t. That's it. Now we're going to work with it and we're going to see what happens. Okay, so I've got 0 equals, now let's replace the sine of 2t with 2 sine t cosine t, and then leave this one alone.
Did you not multiply to 0? Oh, never mind.
Yeah, I'm okay, I think.
Yeah,
Okay, all right, very good. Okay, so what I did is I used an identity again. And you're going to see this some. If you get stuck on a problem like this, start thinking about identities. Okay? Now, let me ask this question. Can you factor that right side? Yes. As a common factor. What's the common factor? Yeah, not the sin, the sine. Okay? All right. So we got sine t, and then you're going to be left with 2 cosine t here, plus 1 there. Okay, so we're going to do like what we've been doing for the whole class pretty much, is now that we have 2 factors, we set each factor equal to 0, and we solve each equation. Okay, like that. All right, now it's basically this one's going to go to a unit circle. You could also do a calculator on this one too if you want to. So this is 2 cosine t equals -1. You can divide by 2, so you get cosine t is equal to -1/2. Now I'm going to do the calculator on this because a lot of times when we're dealing with an application, we wouldn't want to probably say time is pi over 2. We'd probably like to use decimals on this. So I'm going to basically just kind of show you how this goes like this. So if you do, now on radians on this, you'd have to be in radian mode because we want radians, but this problem does go to a unit circle also. So if you did like the inverse sine of 0, well, that gives 0. That's where it is on the unit circle anyway. Okay, so that would give one answer would be time equals 0. Okay, and then the other answer from a unit circle would be at this point -1, 0. So that would be time equals pi. But we don't say pi seconds when we're talking. What do we usually say? Like 3.1 seconds or something like that, okay? So we're going to go ahead and say 0 seconds would be one answer. Time equals approximately 3.14 seconds for another answer like that, okay? So in 3.14 seconds, the pendulum goes back to equilibrium point. Not pendulum, this is a spring. So what it's saying is the spring goes down. Then basically it's going to come back up to that equilibrium point. It's going to do that over and over again. Okay, so there's one other answer of the problem. We're going to do the cosine of t equals -1/2. So if you did this on a unit circle, you would end up being in quadrant 1, and you'd end up being in quadrant 3 because the cosine's negative there. And then you would have to figure out what that angle is. Now you could do that on the unit circle, or you could go inverse cosine of -1/2 on your calculator, and then that gives like 2.09 seconds, okay? And then that's in radian mode, so 2.09 seconds. Okay, so that'd be another answer. Okay, and that would actually be this answer right here. All right, so are we okay so far? Because here's the part where students usually don't get it very good for some reason. Okay, you would have to figure out this reference angle in radians. How do you figure out that angle in radians? It's halfway around the circle, less the 2.09. What's halfway around the circle? Pi. So what you'd have to do is you'd have to do pi, use your pi key, minus 2.09, and that would give this reference angle. So that little reference angle right there is 1.05 radians. So that means when you get your quadrant 3 answer, what do you got to do? You got to go halfway around the circle, then what? Then more, right? Okay, so you'd have to do this. To get that answer, you'd have to go pi plus 1.05. You got to figure out the reference angle if you're going to find the other answer. But you got to deal with that in radians. So the last answer would be this. T is about 4.2 seconds. Usually it's the last stage of this problem that students struggle with, and it's just because you're not used to thinking of things in terms of radians unless they have pi's in it. But it's still the same thing. When I did the inverse cosine back here of -1/2, and if you went to the unit circle, you would get something in terms of pi. You get this, okay? Now, why did that come out in quadrant 2? Because you're doing an inverse cosine of a negative, and what's the range of answers on an inverse cosine? 0 to pi, right? So it gave you a quadrant 2 answer in radians. So what you had to do was you had to do pi minus that to get the reference angle, and you had to use that reference angle to get the quadrant 3 answer. Does that make any sense? If it was in degrees, it'd make perfectly good sense to you. It would, I know. That's why students struggle with that. So the idea is you got to get a reference angle in order to figure these answers out. So again, this was 2.09 radians. This reference angle right here was, now hold on, that was, what was my reference angle? 1.05. Let me ask you a question. If this is 2.09 and that's 1.05, what do you think 2.09 plus 1.05 represents? 3.14. It's pi, right? That might help you a little bit. And then that 1.05 reference angle right here is just halfway around the circle pi plus that reference angle. That's what gives you the other answer like that. Okay, what do you think? Okay, all right, well, that wraps up. I wanted to do this section today because it's a little longer than 4.3.